Hey guys, so let's do some basics about atoms. So in ancient Greece, there was a guy named Democritus, and he said that all objects were made out of tiny, indivisible particles. It's kind of like a beach, right? You can see the beach and you say, this is a beach. And if you zoom in close enough, though, you find out that the beach is made of grains of sand. You could call that one beach particle. And if you put lots of them together, you get a beach. If you put lots of carbon atoms together, you can get me. If you put lots of oxygen and nitrogen atoms together, you can get the air. All objects are made out of these tiny indivisible parts. Now, he didn't know different types of atoms. He didn't know what they were. And nearly 2,000 years later, a guy named Dalton had some evidence to say what atoms are. And Dalton said atoms are these spheres, tiny and indivisible, just like what Democritus said. But Dalton had actually worked out what some of them are, like oxygen and hydrogen, that kind of thing. Okay, so what is an atom? They are tiny, indivisible parts that make up all matter. But there's more going on inside what the atom is. So after Dalton's time, we actually discovered new parts of the atom. We discovered electrons first, and they were small, negatively charged parts of an atom. It was a guy named Thomson that discovered them. So Thomson said, well, the electrons are inside the atom. And so he drew an atom that had electrons inside it, like so. Okay? But then, after that, we discovered the protons and the neutrons and the nucleus of an atom. And they found out that nucleus was right in the center and it was concentrated and had a lot of mass. So went from this type of atom to the idea that in the center of the atom are all the protons and neutrons, and they're really squished together, protons being these positive particles and neutrons being these neutral ones, which I'm not giving a plus or minus. And then Rutherford, who discovered the nucleus, he said that the electrons must be on the outside of the atom, floating around or possibly orbiting around like planets orbiting the sun or the moon orbiting the earth. Okay, this is a decently accurate model of the atom, but it gets better. We'll get to the next guy, Bohr, and his is the atom that we mostly use in this sort of stage of chemistry. So the Bohr atom still has the protons and neutrons in the center, right? That part remains the same, but the electrons are different. The electrons exist in shells on the outside of the atom, okay? There are lots of shells, and there's actually patterns to where the electrons can go on these shells. The first shell can have a total of 2 electrons maximum. The next shell can have 8, and the next shell likes to have 8, although it can have other numbers sometimes. Electrons also start filling in from the first shell, and once that is full, then they move their way up to the next shell and then to the next shell. Okay, so if an atom only has 2 electrons, those 2 electrons are going to be in this first shell because that's the one that fills up first. Okay, atoms are also usually neutral. So however many protons are in an atom, they usually have the same number of electrons. That is to make sure that every plus has a minus to cancel it out. So this atom I've drawn here has 2 pluses, so it's going to have 2 electrons, and they are going to go into that first shell because electrons will always fill the first shell before filling any others. So there they are there. Now these electrons I've drawn a little bit smaller than the protons and neutrons, but really electrons are like points in space, while protons and neutrons actually have size. In terms of the masses of them, the protons and neutrons are significantly heavier, thousands of times heavier than the electrons in terms of how much mass they have. So quickly over atomic structure again. Nucleus has all the protons and neutrons in the center. The electrons are on the outside, and the numbers of protons and number of electrons are usually balanced. So if I add extra protons in here, that means an extra electron is going to be added. That extra electron can't fit in this first shell because this first shell can only fit 2 electrons, so the extra one's going to have to go to the next shell. okay? And this can keep going until this second shell holds up to 8 electrons, in which case the next electron will have to go to the third shell. All right, let's now talk about the periodic table. So let's bring this bad boy in. Sure. This is the periodic table. This is a list of the 118 different types of atoms that we have either discovered or created ourselves. Everything above, I think, 92, so 92 to 118, we've had to create, and everything 92 and below has existed naturally in the universe. Now, there's a lot of numbers on the periodic table. We're going to take one of my favorites, oxygen, and have a better look at the numbers and see what exactly they mean. Right, we're going to copy an oxygen in. Here we go, oxygen. Okay, so this top number is the atomic number. Oxygen's number 8. That just means it's the 8th type of atom. So we've got number 1, number 2, number 3, 4, 5, 6, 7, and then oxygen's number 8. Now, being the 8th atom means it's an atom that has 8 protons in its nucleus. So we can start drawing its nucleus with 8 protons. 1, 2, 3, 4, 5, 6, 7, 8 protons. Protons are positive, so I need to draw little pluses in each of them. Now, you'll notice that there's another number there, 16.0. That 16 is the number of particles in the nucleus of the atom, which creates its mass. Remember, I said electrons are thousands of times smaller, so we don't count their mass really. We just count the protons and the neutrons, and each one counts for about 1. So if there's 8 protons in here, but I need 16 objects in the nucleus, that means there need to be 8 plus another 8 gets us to 16. So I need another 8 objects, and they must be neutrons. So 1, 2, 3, 4, 5, 6, 7, 8. There we go. That is the nucleus of this atom. 8 protons and 8 neutrons in that nucleus. And that nucleus is very, very tiny. Around it are the shells. Now, I can start drawing in some shells. There's the first shell, the second shell, the third shell. There's lots of shells. We don't really need to draw all of them. I don't even need to draw that many. But let's use them to work out where the electrons are going to go. So we have 8 protons. That's 8 positives. So right now we're at 8 plus. I want to get this atom to be neutral because most atoms are neutral. So it needs 8 minuses as well, so that overall it balances out to neutral. Okay, so 8 minuses means 8 electrons. I'm going to start drawing them. You start from the center. So I draw my first electron in the center. And by the center, I mean the first shell. I draw my second electron in the first shell. My third electron, I don't draw in the first shell because the first shell can only hold 2 electrons total. So that's already done. So I've drawn 2 electrons. The third electron I'm drawing in the second shell. Okay, the fourth electron I'm drawing in the second shell. The fifth electron I'm drawing in the second shell. The sixth, the seventh, the eighth, the ninth electron I would draw in the second shell, except there are only supposed to be 8 electrons, so I'm done. I don't need to draw the 9th electron. There is no 9th electron for oxygen. So by looking at these two numbers, the 8 and the 16, you can work out how many protons, how many neutrons, and how many electrons are in any type of atom. The protons are this top number, the atomic number. The number of electrons, if the atom is neutral, should be the same. And the number of neutrons is going to be this bottom number minus the number of protons. Remember, protons plus neutrons equals 16, equals the atomic mass. Okay, hopefully that's cleared some stuff up.